fix bugs you can't reproduce? Capture one trace row and replay the whole incident exactly. By the end, you will see how a single stored trace can become a full replayable incident, so you can debug and regress real LLM failures reliably. I'm Professor Pi, teaching AI engineering and LLM systems with simple Python. Many teams lose hours chasing bugs that happened once. An LLM returned a surprising answer, or a call timed out, and no one can reproduce it. Failure replay turns a single logged request into a deterministic experiment you can run anytime. That makes debugging faster. It also lets you turn incidents into regression checks, so the same bug does not reappear. At a high level, the idea is simple. Persist one structured trace row with the request and response. Extract the minimal inputs needed to call the model again. Run the call deterministically or with a controlled simulator. Compare outputs and record the result as a test. If you can do this inside a local queryable store, you get simple auditability and repeatable runs. We will build a tiny pipeline that logs a trace into DuckDB, extracts a replay config, picks a single failing incident, reproduces the result with a deterministic harness, and then writes regression tests back into the database. This keeps everything durable and queryable and makes debugging feel like running unit tests. Now, we will create the persistent trace and insert one row. This snippet creates a tiny, structured log for LLM requests in DuckDB. The connect call builds or opens a local traces.duckdb file so data persists between debugging sessions. The create statement defines a compact schema, a timestamp column T, and a JSON column J that packs the full request and response details. The insert uses a parameterized query to write a single trace row with prompt, context, model, temperature, limits, response, latency, and status. Finally, the select count confirms persistence by returning the total row count. Seeing one inserted row verifies you have a durable, queryable incident log. Next, we will derive a clean replay configuration from the logged row so the stored JSON becomes a stable input for replay. This example appends a failing incident into DuckDB, then derives a clean replay configuration from that single row. The insert adds TR2 with the prompt, context, model, and generation settings we will need. The query uses JSON object to assemble a stable config containing prompt, CTX, model, temp, top P, and max tox extracted from the J column. The JSON keys function returns the field names so you can verify the replay surface is complete without leaving SQL. If you trim fields, the key list shrinks. Adding fields expands it. The printed keys confirm we captured all inputs required to faithfully reproduce the call. Now we will pick which failure to target when there are many incidents in the table. This code narrows the incident list to a single actionable failure using DuckDB. The count query is incidental bookkeeping, while the main query filters for rows where the status field is fail. It extracts the trace ID and latency from the JSON payload, then orders descending by latency to prioritize the slowest incident. The fetch1 call retrieves the top candidate for replay. If you change the order clause to ascending, you would target the fastest failures first, which may reduce reproduction time at the expense of missing worst offenders. The printed ID and latency tell you exactly which failing trace to replay. Next, we will turn that chosen trace into a deterministic check and compare the logged output with a controlled model run. This snippet turns a single DuckDB trace row into a reproducible check. The first query selects the highest latency failures ID, so the harness targets the right incident. The second query fetches the stored temperature and the logged response for that ID. The variable got simulates a deterministic model output that flips at a temperature threshold after rounding to 1 decimal, mirroring how small config differences can cause drift. If you increase the rounding precision, mismatches can appear. Decreasing it makes the harness more forgiving, but may hide real bugs. Seeing matched true means your replay harness reproduces the logged response. Now we will promote the single run harness into a persistent regression suite, stored alongside the traces. This snippet elevates replay into a persistent regression test suite inside DuckDB. The function replay LLM is a tiny deterministic stand-in for your model, and create function exposes it to SQL. The create table statement writes a tests table comparing the expected response in the trace against the UDS output for each failure. By pushing the comparison into DuckDB, you can run many replays with a single query and join them with other monitoring data. Tightening the rounding inside replay LLM will catch more subtle drifts at the cost of flakiness. The printed count shows how many failing incidents now pass as regression tests. Mapping this toy into a production flow is straightforward. Replace the deterministic stand-in with a controlled model client that accepts the saved config. Keep the storage path, traces DuckDB, or swap to a shared store. The same comparison logic scales to batches of incidents and becomes a nightly regression sleep. Recap. This approach logs a single structured trace row and turns it into a replayable incident. Use it when you need reliable reproduction and a way to convert failures into tests. One caveat: making the replay too strict with precision can create flakiness, while making it too loose can hide real regressions. Next step: tighten or loosen the rounding precision inside the replay harness to balance sensitivity and stability, and rerun the regression sweep. If short, practical AI engineering helps, subscribe and watch the AI engineering videos.